We now move to our sixth speaker. Introduce you properly. Professor Seth Snyder of the water, he's the water initiative leader of Argonne National Laboratory. He's also an adjunct professor of mechanical engineering and chemical and biological engineering at Northwestern University. He has been involved in accompanying our work and our project from the very start. It's a pleasure to introduce him, and his topic would be the state of technology for producing clean water. Seth, bevakasha.
So I actually have a huge advantage here from Professor Cohn's talks and other talks. Pretty much everything I was going to say has already been said. So I could actually just go rogue and do whatever I want because I have a half hour and I don't have to say anything. But first of all, I wanted to say, this is a little loud. Is that there's fresh coffee and there's cookies, and I have no problem if people go up and get some coffee and cookies right now. So go on ahead and all. But the other thing I want to say is that we're at a university here. I mean, I have gray hair. There's a lot of gray hair folks, but anytime at a university, I think that is our primary audience. Anybody here, who's a student here? What's your name? Vania. Why did you come today? Oh, so you just came for credit. You didn't really, all right. One thing good is when somebody's honest. You came just for brownie points. That's fine. That's totally fair. I do the same thing. So anyway, I'm here to talk about technology, but I'm going to put a little bit of lead in on this. Professor Packman is a professor of environmental engineering, and I gave a talk a couple weeks ago talking about the environment, and I entitled the talk Environment, April 22nd, 1970 to November 18th, 2016, RIP. And do people remember what April 22nd, 1970 was? Very first Earth Day. We are going through a big reset in the US, and I'm going to primarily talk about the US in this, because this is important. We're going to go through reset. We are going to come through this. We're going to come through, it's going to look different, but we're going to have some shock. So I did spend yesterday afternoon looking at very, very small numbers. And what was I looking at? I was looking at the fiscal year 2018 proposed budget and research. And so programs that have been very important to me that I think can make a difference in the world. So as an example, there's one that's in Department of Energy's Biological Environmental Research, in which they have a big program, an integrated assessment, understanding the impact of climate on water and that relationship to energy. That budget in fiscal year 2017 that was only passed 2 or 3 weeks ago was $17 million. The proposal for fiscal year 18 is $2 million. So a 90% reduction. I am working very closely with Professor Cohn on what we called a Clean Water Innovation Hub. That budget was in there 2 weeks ago at $20 million a year. The budget for fiscal year 18 was zero. It's just not needed. So we're going to go through a reset. We will come out of it, but this is very important. So I work at a place called Argonne. We talked a while ago, we saw a picture of some famous scientists. So there's some famous scientists here. This is the founder of Argonne in there. I don't know, where's the green? Oh, I see it. This is Enrico Fermi. He was the founder of Argonne National Lab. He did the first control rods fission. It was done at, there's another university campus. It's right on the south side of the city, but I forgot the name of it. But anyway, this was down there. And actually, we had hanging at Argonne a letter in which initiated, it was from that same guy, Albert Einstein, wrote a letter to Roosevelt. We may have a way to harness energy from the atom to make a weapon that could control, that could be devastating in World War II. So that was the initial of it. And part of the reason it was done here in Chicago was because we were away from the coast and we didn't know what was going to happen in terms of attacks and all. So there was a reason it was done at Chicago, and it was called the Manhattan Project. But it was done by Enrico Fermi, and he was our founding director. So we still go on. We are an energy lab. We're not a defense lab. We're not a nuclear lab. And all. And here's some quick numbers on us. We're close to an $800 million a year budget. That number will be smaller next year. I don't know what it'll be, but it will be smaller. That's the only thing I can guarantee. We have 3,000 something employees, 1,600 scientists. So we're a big driver of innovation and intellectual capital brought into the region. And we'll be affected by that. We have lots of postdoctoral researchers. I've had dozens of postdoctoral researchers who's worked for me. This is at any one time. We have 300 now over the team. And we have lots of public user facilities, which is your tax dollar helping to address a variety of science missions. So, but that is not what we're here. We're here to talk about water today. We heard a couple things all over the price of water when Professor Cohn was talking. When is desalination affordable? This is a question I ask students and I ask people all the time. Ellie, what do you pay for a gallon of gasoline? Me? Yes. Where? at the corner.
$2.89.
$2.89. What did you pay for water?
This is a tricky one. I have to think.
Exactly. So, and I ask that question everywhere I speak, and everybody knows the price of gasoline to 3 significant figures. And there's a few engineers in the room, but nobody knows the price of water to 1 significant figure. We have no idea. How do we control use? How do we talk about cost? We don't even know it to 1 significant figure when we know gasoline to 3 significant figures. That is an important question and all. And that is part of the issue for how we control it. So gasoline is, I don't know if it's $2.89, $2.51, it really doesn't matter to me. Around here, water is about $3.50 for 1,000 gallons. So it's way smaller. And sometimes you get numbers all over the place. And I ask students that all the time. But if we don't know the cost of something, we don't know the value of it, we don't know how to control efficiently. So a lot of what went on today was because people have no idea how to answer that second question. Yoram, do you know the price in California?
For what? Gasoline?
No, either one. This is the world expert. What's the price of gasoline?
For gasoline, it'll vary between about $2.90 to about $4, depending on where you are.
All right, on your corner.
In my corner, it's about $3.10.
Oh, and how about water?
Water is not sold in my corner.
Okay. So he can't even, I mean.
But I can tell you, water in our district goes for about $11, $12 for 1,000 gallons.
Okay, 11, 12, so about triple here. Nobody has any idea. So that is the importance of it, but what I think is, when I started off talking about environmental, I think this is the nexus of where we have to go. I'm going to talk about water and then society. These are the 3 things we think about with water. This is the nexus of water. We can have quality, we can have quantity, we can have price. Pick 2. Whichever 2 you want. I can give you lots of water at low quality, or I can give you lots of high quality water, but we have to pay for it. And when we talk about technology, when I think about technology, I'm trying to basically optimize, do a Pareto optimization around this. How much do you need at what quality? And then I can define the price for you. It matters what the inputs are, what the outputs are, and we'll talk about that in a few minutes. But you only get 2 of these 3. But when we talk about honesty and science and technology, this is, I just picked 3 things, but this is the guiding principles. We have statistics, thermodynamics, we have evolution. You get to use all 3. You don't have a choice, you have to use all 3. So when we talk about science and all, we have to use that whole boat. We can't, politics is politics, but science is science, and that has to be a core part of what we do. So when I come up with analysis and I do technology, I'm doing the best I can to be objective, but I can't make believe the laws of thermodynamics don't exist. They exist, they're going to exist now, they're going to exist 10 years from now. I have an old colleague of mine, Richard Doctor. He used to do lots of Aspen modeling, get energy balances and all. The energy balance you got from an Aspen, that was the energy balance. It wasn't like a matter of interpretation. I mean, that number was real and all. And that's important to think about. We could do the same thing biologically, mathematically. We could put a lot of other things up here like quantum mechanics and all. I just wanted to have 3 on both lists. So what is happening with water in our challenge? So water really is the crux of climate change. Earlier in my career, I spent most of my time working on energy. And when you're working on energy with an environmental hat on, you're thinking about how can I mitigate, how can I avoid the risk of climate change? When you work on water, you have given up. You're saying those forces are beyond your control. How could I adapt? How can I manage it to minimize the impacts? And when we think about it, most of the impacts of climate change have to do with how much energy and how we use energy. There's other factors in there. But most of those impacts of climate change are on water. whether it's drought in one area, which we're talking about in the Middle East, or flooding and stormwater in the Chicago region and all. And when we look at it, so that's really an important crux. The World Economic Forum, which we also call Davos, they have looked, every year they look at risks, and water is always at the top in terms of likelihood of and how big the impact is. So it really affects both. It's highly likely it can have large impact. So I think this is important. I'm going in my career, I'm going to spend the next couple of years working on water because I think it's important for society. And it's important because we've lost our message in environment, but it's necessary to do. And I think this is one way to go about it. So one of the things I'll say is water is big. A friend of mine sent me this cartoon. These are little pipelines that if you wanted to send, just say, all the ketchup through the world, it would look like that. And that's all right here. But if you wanted to send the gasoline, it would look like that, and that's petroleum. This is the pipeline for water. So water is really big. I had some discussion at lunch, fuels are such a big market and all. The U.S. Petroleum industry, we move about 19 million barrels of oil a day. That's the entire U.S. economy uses about 19 million barrels of oil a day, and we're the largest in the world in terms of use of oil. But if we look at that Jardine drinking water plant right off of Navy Pier, that actually is moving about 20 million barrels of water a day. It's something close to 1 billion gallons. So that one drinking water plant in Chicago moves more fluid than the whole oil industry. I know the oil is worth more, and that's part of the challenge. And when we think on the other end, MWRD, which is a water reclamation district, they have the Stickney wastewater treatment plant. It's off near Midway Airport and all. They have the capacity, and it depends on how much storms, how much rain, to move close to 30 million barrels of wastewater a day. That's what they're treating, and that's versus 20 million for oil. So this infrastructure question. So we hear a lot of the news about the question of infrastructure. Infrastructure and water are very, very they are the same thing in many ways. Water infrastructure is critical. I don't have any slides on it yet. I'm always updating my slides. But you look at civil engineering reports, we hear about states of bridges, and we know that we occasionally have bridge collapses or we have bridge failures. They get about a C-. Most of our water infrastructure gets numbers in the D- range. So when we start talking about we need to make infrastructure investments in the U.S., water is core to that. And you could look at numbers. I think I pulled a slide out on it. No, maybe I didn't. Is that depending on who you look, the U.S. needs about a $4 trillion investment in its water infrastructure over the next 20 years or so. Not per year, over the next 20 years. That is actually about the size of the total federal budget. So if we were going to really invest in water, it's not a total federal, it's a public, private, and state, and all that other kind of stuff, is that this is a very significant number. This number comes from the consulting firm Booz Allen. If you look around the world, it's a $20+ trillion investment is needed in water infrastructure. The challenge is this. Do I have anybody from the water industry here, not researchers? I saw MWRD on the list of invitees. I didn't see anybody show up from there. Is that these are very risk-adverse industries. So a lot of the work we do is how do you get technology deployed in industry? That's a very important question. And they are very happy to be about the 18th person to deploy 25-year-old technology. It's a very slow-moving industry. It's extremely risk-adverse. It's very low margins. Nobody knows the price of it, and so nobody knows the cost, and so it's hard to get that investment. And so it is typically very capital limited. They don't have the dollars that need to do it. So if you go to a typical water utility, their real capital budget is really an operating budget. A pump breaks, we fix it. This breaks. Nobody looks and says, what should we do to use money smart over the next 20 years? That is a hard thing to change. Doing a little bit on that, and if we do things like do big investments in research, that's what we hope to change. But that's a hard question to change in terms of deploying technology. So how do we use water just in the U.S.? We've seen a lot on the Middle East, so I'm going to focus just for a second on the U.S. Yoram discussed this a little. So we have two things with water. We have withdrawal and consumption. Withdrawal means we take it out of a source and we put it back at the same source. That may be a different quality, but we don't consume it. And consume it means basically we take it out, we don't put it back. So what is obvious pretty much everywhere that agriculture is a dominant player when we're talking about consumption. Israel does it far more efficiently than the US, but we typically do not return waters, from agriculture. But in the US, the dominant withdrawal of water is for something most people don't expect. It's for cooling thermoelectric power plants. So why me, as somebody who works for a Department of Energy lab, do I focus on water? This is ground zero of this, is that the single largest use of water in the US is for cooling power plants. And so a reliable power grid requires a reliable water system. And so that is what is called the energy-water nexus. And I won't spend a lot of time on it. Some talks I give, I have like 20 minutes talking about the different interfaces there. But that is ultimately why water and energy are linked together. Professor Cohn talked about the energy use for desalination. That's part of it. But this is the ground zero, is that reliable power sector requires a reliable water supply. Any questions yet?
Perhaps not a question. I'm sure you can clarify for everyone. When you talk about thermoelectric, it's not all consumptive use.
No, it's not. It's withdrawal. So I didn't go. So that means. So yes. So withdrawal means you take in. Just say you have a power plant in a river. It comes in. It cools the power plant, and once through, it's returned a few degrees warmer. That does not consume the water, but to have that power plant operate, that river has to be flowing. And if the river temperature rises, then they have to degrade the power plant. I did leave that out. That was a good point.
Aren't the further use of fossil fuels really engaging our Great Lakes water supply, like the Enrich Line 5 pipeline over the back of the United States? If we don't really convert to renewable energy, we threaten to cause havoc to our Great Lakes water supply. That pipeline was.
I don't know much about the pipeline, but the questions about reliable water supply and power is something we're deeply embedded in at Oregon and other places. And we have actually a big proposal pending at DOE, except for we don't know what's going to happen with the budget, to focus on that question, the reliability of the power grid based on water focusing first on around the Illinois River system, but then going into across the upper Midwest. That is an important question that we see, and we're trying to get that project launched right now. So ultimately, when we talk about water, and we've been talking about a big region, the Middle East, difference in the U.S. and the Middle East is that not everywhere is regional, is that we have enormous amount of variations. So I interact with folks at an organization called the Metropolitan Planning Council. They're downtown, and you talk about water, them flooding. The only question about water is how do we prevent it from getting in people's basements? If Professor Cohn's in UCLA, it's how do we have enough water? It depends on where you are. In the southeast, in Atlanta, we've had power have to go offline because there was not enough cooling water. So every place is different. And we obviously know in drinking water, in all the upper places, we heard about Flint, but Chicago is very bad, the age of the pipes and all. So water is a regional question that has to be solved. So one of the questions people always ask me, and it came up this morning, is how much does it cost to do this or that in water? And the answer I always give is it depends. How much water do you need? At what quantity? What price you want? It just depends. What's the input? What's the output? There is no answer. At lunch, I had lunch with Professor Coe, he leads the Solar Fuels Institute here. I don't see him here this afternoon. Power is power. I mean, it's not as simple. It's not that perfectly simple. But if I could build a PV system and I know how much sunlight, I could tell you how much it's going to cost to deliver power. Water, everything is regional. Depends. And so Israel does it, and I'm going to really skip over the Israel stuff because it was covered much better than I ever could. Israel does it very differently. Israel, it's national. We've seen lots from all the other speakers about how the system works, how we have a national water carrier, how we flow. It goes from Sea of Galilee, the desal plants, and all. So I'm not going to go into this. But in general, water scarcity is driving desalination. We heard a lot about that from Edith's talk, from Yorm's talk, and others. But this is considered a large market, and like Yorm, I'm going to focus on one aspect of this as we get into the technology side. I'll talk generally about it, but then I'm going to talk about something different than seawater desalination. So this was talked about, so I'll skip that. So how does desalination work? When I went to Aaron, I said, I'll talk about technology, and I thought about the audience and all. So I'm going to do it a little bit technical, but it's not going to be super technical. You can do it probably my talk right now, because he's an undergrad of mine, a very talented young man. So what is salt is the first thing, sodium chloride. But what do we have in the water? So we have mostly sodium chloride, but we have other salts in there. We have calcium as mentioned, we have magnesium, chloride is primary when this is carbonates, we may have sulfates, and they're approximately, in drinking water, approximately 1,000 ppm, 1,000 parts per million. We have nitrates a little bit lower. This might come from ag runoff and all this. We want to limit that. Most places 10 ppm is about the limit for health reasons. Then we have some more nasty elements in there, cadmium, arsenic, chromium, and these are much lower. And if you go one step beyond that, I've done a lot of work on the Great Lakes and mercury, and that gets down into the parts per trillion level, so that's down a whole nother level, and that's a pretty bad, nasty mercury because it bioaccumulates and all. So what is that basics of this? So this is desalination 101. Professor Cohn went way beyond this and all, but basically we have feed water that has salt in it, and we want a bucket with no salt in it, and this bucket with lots of salt in it. That's as simple as it gets. We have, there's a lot of discussion of the thermodynamics of it. You can look at how much energy thermodynamically, and at the same time you look at the water recovery rate. Most people think about desalination. They think about how much energy, but as Professor Cohn said very, very well, is that water recovery rate is very critical. And what we notice at this point, when you get down to very high water recovery, energy goes up. What's happening there? That at the very end, suddenly the energy goes way up. That concentrate salt is getting really, really concentrated, so it takes a lot of work. Professor Cohn mentioned osmotic pressure as you have higher salts and all, and it takes more and more pressure to do that with most systems. And so that kind of gets to that limit, and this becomes the discharge, what you have to discharge, in some way, sort of waste system. So typically this feed solution is this large source called the ocean. It's 35 grams per liter, which is 30,000 to 35,000 parts per million. It's the most common feed water, of course. Its main issue is salinity and the energy cost. And we see the energy cost is manageable. It'd be nice to be lower, but we have this rule of thermodynamics, and that's what I said at the beginning. We can't break the rules of thermodynamics. We have lots of it so that we're not limited there. Brine management's relatively easy. We could disperse it back in the ocean. And you know what? That salt just becomes a drop in the ocean. And so it's actually relatively straightforward. Oh, sorry, I don't know what I did. Oh. So I'm interested in questions about other types of water. We heard some groundwater questions and all, and I'm going to call this 2 to 10, so about 2,000 to 10,000 parts per million brackish water. We have the salinity there. We have much less. We don't have nearly as much water here. So you'd think, okay, this is not as useful. But I'll tell you, this is far more dispersed. We have no seawater in Illinois whatsoever. No matter where you look in Illinois, we have no access to seawater. But we have lots of groundwater and various industrial processes. This is far more distributed in terms of a use. So if we're thinking about society, it can solve many more problems, even if there's not as much of it. So this is a very important opportunity, and this is where I spend a lot of my time right now. Some of the challenges is brine management. So I get that concentrated salt motion. I don't have a drop. It's not a drop in the ocean, and you don't want to put it in a river. You have to really manage it. Professor Cohn mentioned that one option is injection. Who knows what happens when we inject lots of water down in Oklahoma? Induced seismicity. It's not always it depends on where you are, what can be done and all. So you have to think about that question differently. So one of the things that I think about in this is how can I get that volume as small as possible? You don't want to just lay it out in an evaporation pond. That takes a lot of land, and there's a variety of reasons not. But can you concentrate that salt so you have as little waste as possible and then go from there? I'm not going to. I had done some stuff on really concentrated stuff, so this could be, water from this could be produced water or extracted water. This could be a variety of industrial water processes, super concentrated, that's usually done in evaporation ponds. I'm not going to talk about that, technologies in that today. But how does a desalination plant? I'll largely skip it. We take in some water, it's diffused. We do some filtration and pre-treatment as mentioned. We do those reverse osmosis we saw in Yoram's lab. He has these desalination, our reverse osmosis units, and we do some treatment. We send the water to the people, and we send the salt dispersed back into the ocean. The old days, so we heard a lot from Nita and others about talking about across the Middle East. Most of the Middle East uses a distillation, a multi-effect, or different kinds of distillation. They are basically using a thermal process to generate clean water. It's actually lower capital cost. This is a much older technology, and it works okay, but it just requires a lot of energy. So if you're at a place that has lots of, just say, you're producing oil and you're getting natural gas and you're flaring the natural gas that's generating heat, there are a lot of opportunities if you have excess energy, and there is many places in the world that have excess energy, to use that to generate the clean water. This is used in many places in the world. It's not going to be used in the U.S. in general. It's not going to be used in other places. But one of the critical things is when we think about reverse osmosis, which was somewhere on here, and the distillation, is what are these processes doing? When we talked about the reverse osmosis, you're pushing the water out of the salt. What are you doing with distillation? You're boiling the water out of the salt. In both those cases, you're removing the water from the salt. You're removing the water from the salt. That water, if it's seawater, is 3% salt and it's 97% water. So we're taking a mixture and we're taking the 97% out of the 3%. That's part of the reason why it's high energy use. I'd say the same thing here. It's basically, I've got my slides mixed up. So basically, it requires pressure to push that water out, but what we're doing is that we're removing the water from the salt. And this is where I'm going to go to a technology shift here in a second. And that's really where the energy burden is. So one of the challenges is this: when we remove the water from the salt, if I have 30,000 versus 10,000, it's about the same amount of energy. So there's no benefit to using less salty water in terms of total energy. I'm going to talk about doing it the other way around. I am going to talk about doing this oppositely. Instead of removing that 97% water from the 3% salt, if it was brackish water, 99% water from 1% salt, I'm going to remove the salt from the water. So this is a technology it's called capacitive deionization. So this is being developed in a few labs. It's not commercial yet, but it's getting close. And these are slides from my colleagues at Lawrence Livermore National Lab. What we're doing here is that, and this moves in a second, is that we basically have a system where we have porous electrodes. We're flowing in the salt water, and it just kind of flows through. When we put a charge across this, the salt are all ionized, so the anions, which are chloride, and the cations, which are sodium, stick into the membranes, stick into the electrodes, and so it desalinates it. And that's a nice thing. So let's see, I think this works. So no field, we put the field on, and it grabs all the salt. The water flows through. What happens then? After a while, we reach capacity. We can't hold any more salt in. We shut off the electricity for a second, the salt flows out. So it's just a matter of plumbing. We have to see desalted water while it's building up, and eventually, when we shut off the field, the salt comes back in and we just dump the salt out. And so we can get a much more concentrated salt. But the critical thing here is that we're using electricity, but we're taking the salt out of the water, and we're not taking the water out of the salt. So it's a different approach to this. And the advantage I say in this is not for seawater desalination, but for those brackish and those intermediate grades. So this is a different way to go about it. So is there research on here? What are the research is on what are the materials, what are the design? There's a lot of materials, engineering, design work in here. This is a very exciting field. And so as I said, that we remove the salt, the brine. When we look at capacitive deionization, when you're up there at seawater concentrations, it actually takes more energy than reverse osmosis. But when you start going down to brackish and all, when you're going down to lower concentrations, it gets more, relative to reverse osmosis, gets to be more energy efficient. Because reverse osmosis is relatively flat, and since we're removing salt, the less salt in there, the less it is. So the critical thing here is now is when we have those intermediate grades of salt, suddenly we have a solution that has a potential to be way less. It uses less energy. I haven't proved that it costs less yet, but that's where we're going. And so some of the advantages, are that we don't need the high pressure, and pressure costs money and takes energy. I don't think this is totally true. It's fairly, it's the size it doesn't matter. I think they're relatively size independent, both of them. This can be fragile. This is where there's research. This can be very robust materials, and depending on the electrodes and all, you can preferentially start selecting things out of there. And there were questions earlier today, and Adjunct, when he did a research project, can we selectively pull things out? You do have the potential for selectivity because we have a different type of material. So I'm now going to talk about another technology. So that was not worked on direct. My group is doing that a little now, although these slides are from Lawrence Livermore. This is work directly coming out of my lab. This is a unit we call electrodeionization unit. In specific, we call it a resin wafer electrodeionization, or READY. So READY is actually now the name of a spin-off company. My postdoc formed a spin-off company on this, but we're continuing to do this work. Once again, like with capacitive deionization, the thought process I put in this is I'm going to take the salt out of the water. I'm not going to try to take the water out of the salt. I'm not going to use pressure. I'm going to use electricity. When we do that, we find very specific applications. We think it's very good for brackish water, produced water, which is water that comes up when you do natural gas, and it's very good for things like recycling of cooling water and for water in cooling towers, all these intermediate grades. And so how many desalination plants, for seawater desalination plants in the US are? I don't know, a handful. There are literally 15,000 or more cooling towers in the US. So this is a lot of potential applications. So how does the technology work? We have a system. We have a material here, a resin wafer, we call it. This is a parallel stack. We again have electricity, we have flow, and essentially we're using what we're calling a technology, electrochemical ion exchange. So again, we're using electricity, we're binding salt molecules out of it, we're separating them out and all. We can tune the properties to enhance performance and consistency and all this other kind of stuff. And we can add all sorts of functional things like chemical catalysts to do reactions to clean up specific species. So if you had an organic molecule there, we could probably react it and make it into a salt so that it would come out. So we're doing a lot of tailoring and design around this and all. In the process, like with the capacitive deionization, I'm not so fancy, mine don't move, is that we have a salt stream that moves into here. This is the resin wafer. It basically is a really nice home for ions to bounce around on and electricity to hop across. In the electric field, there's an electric field here. The cations, so the sodium moves one way, the chlorides moves the other way, and they concentrate. And here's the important thing in our technology. Unlike reverse osmosis, where we have an osmotic pressure, we have a proton motive force. That electric field is keeping those salt molecules out. So in this concentrate channel, which just recirculates around, we can keep concentrating the salt. We estimate we can get that salt up to 30 to 40%. That may be pushing it, but at 30 to 40%, we are now at 300 to 400,000 parts per million. Whereas typically we don't think with reverse osmosis we'll go above about 70,000 or so parts per million. So we have reduced the volume of that brine by at least a factor of 3 or 4 versus reverse osmosis. And this is starting from a dilute thing. And so when you look at recovery rates, we're looking at, with this technology, recovering 95% of the water effectively. And all that makes, so we're severely reducing that amount of brine, which if you're inland, is a big barrier to deployment. So that's how we're thinking in this. So it's a different way to think about the technology with a similar sort of goal. How do we provide clean water sustainably and economically? I won't go through. So my graduate advisor told me, and apologize to all the other speakers on this, if you have one slide with numbers and equations, you have one slide too many with numbers and equations in a talk. But my one engineer insists on this. But anyway, we're looking at the energy consumption numbers and the size of the system and the water recovery rates. We're doing all that analysis right now. And we have a good idea where our technology makes sense versus where existing technologies make sense. And we're also doing deep dives on what type of systems. So in the Southwest, which is much more like the Middle East, it makes sense for a variety of reasons. It has to do with the hardness of the groundwater and the availability and the cost of other sources of water. And I'm going to close just with a simple and straight plug that has nothing to do with what I talked about before, is that right here in Chicago, we have 84% of the fresh water right at our doorstep in the Great Lakes. We have used that and made the case that water should be an important part of a research program here. So with Aaron and my friends at University of Chicago and University of Illinois and the local utilities, we formed a nonprofit group called Current. And Current was launched and is just getting up and running. So we have a nonprofit, it's a 501c3, to promote water research in this region. And is Steve still here? Steve is sitting there in the corner, not you, Steve Frankel. Steve Frankel is the executive director, and Jackie's our communications director. So we're just starting research projects right now, but it's really saying that water is something we should do big in Chicago. Chicago's been a long history in this region of water research and all, and we're rebuilding that right now. And so, thank you, and I'll answer whatever questions I find. That, by the way, is a shameless plug. That is my daughter, and that's my nephew. And that's Lake Michigan. They're happy to be near a large freshwater source.
You're on.
Yeah. Is this on? Okay. Can you hear me? All right, very, very nice talk, and I just wanted to either point out, or maybe you can speak to it. One of the things that often we forget with respect to comparing the technologies, while we're talking about removing salts, we have to remember that there are a lot of other things in the water. Mm-hmm. And so RO provides you, and I'm not promoting one technology versus the other, just pointing to differences. Just promoting differences. We've done work on various technologies. RO provides you with basically a multiple barrier against multiple contaminants, which the electrical approaches do not, because what you're doing is you're removing the salt, but you're not removing all the other components if they are in the water. Yes. And so in order to remove those, you're going to have to pay energy, because separation is not free. So at the end of the day, the application specificity is going to be very important.
I wholeheartedly agree with you, and one of the things is, I didn't go into details here, so what we do in some of our electrochemicals, we do a pre-treatment, we might do a micro and ultrafiltration, and also, there's no simple, here's the box, it solves the water problem. It's always an integrated system. It always depends on that quality. I say that from the beginning. Everybody asks me a question on water. Well, what's it going to cost? It depends. What do you need on the out? What do you got on the way in? And also it depends. But if the energy barrier is removing the salt, that's what we're trying to address there. And one of the things is people argue with me, and I've done investor presentations and all. You got to have a solution that works for everybody. I said, nothing in water will work for everybody. If somebody, for my lab, occasionally people will propose a water technology. The tech transfer group will ask me to analyze it. And the first thing the person will say to me is, I have a technology that removes everything from water. I said, what comes out on the other side? A vacuum? I mean, it always depends. It's much more complex. than that, and you're exactly right. One of the things, and sometimes they use it in conjunction. How many students here work in a wet lab? Man, this is bad. I mean,
They all work in dry labs.
I used to go home at the end of the day when I was a graduate, and I stunk, But if you have a millipore system in your lab to provide lab-grade water, do you know where if you open up that box, it's got a reverse osmosis and an EDI side by side? So these technologies do work together. And I agree, the ultimate solution will be integrated, but we can only work with the context of understanding that we're part of a system, but we work on an individual unit operation at a time. And one of the things in a big center is that we do it together, which is what we're working to achieve.
I got lost pretty much at the beginning.
I got lost about 5 years ago.
But I would like to ask you to repeat something I thought you said. If you're working on water, you're working on something where the message is being lost?
Okay, so I try to say controversial things, and I hope that starts people to listen. What I said is I spent about 15 years when I worked with Richard, always working on energy. And every morning, Rich and I would come down. The reason we were showing up is that if we manage energy better, and we worked on renewable energy and energy efficient projects, we're trying to avoid climate change. We're trying to reduce CO2 emissions, which are primarily driven by our energy use. If you work on water, that is not going to reduce. You could talk about small ways. It's not going to reduce CO2 emissions. So you're not working to avoid climate change, but you're basically saying climate change will happen, and I've got to come up with systems that society and the environment adapts. And so basically, by working on water, I'm basically giving up on society and say we have to come up with solutions because it's going to happen. And you may or may not believe me, but I got to start a talk somewhere.
Water is such a, as you went on to say, it's so important. How can you not be interested in working in water as opposed to working on energy? So I misunderstood.
There's so many questions in the world that we all can work on. I mean, why shouldn't we all be working on health? I mean, that's another fundamental thing, But we only have so much brain power, so much bandwidth, so we only can do what we can.
I have a couple of questions, one political and one scientific. A couple of years ago, I had a conversation with Gideon Bromberg, who's the Israeli co-director of EcoPeace Middle East, and I was asking him if there was a possibility of using the solar energy farms in the Negev that were founded by the Ben-Gurion University to transport that energy for solar energy for desalination. And Bromberg told me it can't be done because the fossil fuel interests in Israel are too powerful to allow this conversion. I wonder what you might think of that. The second technical issue was I was interested in what the network of those porous electrodes were and how much we understand now the transport of those ions through the porous network.
Okay, so the first question is on the power industry. The Israeli power industry had a complete transformation because it was 5-10 years ago, it was 100% dependent on coal, and then natural gas was discovered. And I think it's, Steve Frankel, is it 70% natural gas now?
Very substantial.
I mean, so they had a complete transformation. Do you have embedded capital? Yes, you do.
Yeah, but methane is 100% more potent as a greenhouse gas than CO2.
It's actually it's about probably more like 1,000%, but that has to do with the emissions of it. But methane is much cleaner to burn than coal. It's about if you burn efficiently, you get about half as much CO2 from methane as coal. But what I'm saying is that the industry won't change. The industry will change. I don't know the politics of Israel that well. I do know what happened in the power sector because my cousin actually was the engineer in charge of deploying those plants. So that's just what I know. Yeah, there's always, in the U.S., which I know better, there is always that push and take. So right now, Exelon has basically gotten through the state that we're going to have subsidies on the nuclear, and they've been pushed back because of the stresses on wind. So wind has gone from essentially 0 to, it's about 5.5, and some people think it'll go as high as 20%. that decreases the demand for that. Yeah, I mean, that is a political question and all, but that's way above my pay grade, you know, as the saying goes. But that is a part of a question, you know, in there is how do you get that across? California is different than Illinois. Illinois is certainly different than you know, states to the east and south. And we've had a pushback on that. We've had, you know, RPS requirements. So we've also done some complexities here, just say in Illinois, which I know best. We had an RPS, which stands for Renewable Power mandate. We had that phase in the exact same time that we actually had a decoupling, where the city of Evanston can go and buy power from whoever they want. And these two things work completely oppositely, because the city of Evanston can negotiate for somebody who does coal and buying electrons from coal in Iowa. At the same time, we had a requirement that a power had to be renewable. So yeah, the politics are hard. And one of the things I teach, one of the courses I've taught here the last few years is called Introduction to Sustainability. The class is half engineers and half social scientists and journalism people, and I've had art history. And what I think is very important to do is that you want to have an honest and objective, you know, discussion based on facts and based on what's that impact, and not obscure the facts. And I think one of the things I try to do in whatever the audience, and I said lots of gray hair people, the people you need to influence is the students. And one of the things I talk about a lot is don't tell me how you're going to convince me of something. Tell me how you'll convince your parents who are not scientists, or even your grandparents who may not understand the details. That is a very important message for us to make progress politically. It is a hard question, and the only thing I know is from what I read from books. I have no training or particular expertise. The question on the electrodes, though. Those are carbon, that's not directly my work. We're working on different materials. There's carbon electrodes, there's things based on MOFs, which is multi-organic framework. I know much more about the EDI technology. That's where I've been deeply embedded. But it's a question of materials that will absorb, you know, ions quickly and then desorb them. So you want to have high capacity to absorb, but the ability to do that exchange quickly. So we don't want something that basically deeply embeds ions into the material. So the exchange rate, we don't want to have to force it out. We want them to just diffuse out. And if you want further information, I'll give you my card, and my colleagues have a lot of papers on this subject. We're just writing our first papers on it now.
When you were talking about the desalination process and like giving back the salt to the sea, and that it was like none, is it really none, or it's like an impact that will be like in a very long term, like giving back the salt, you're not like...
So will desalination of seawater affect the ultimate levels of the sea in terms of salinity?
Yeah.
I think only in hyper-local places if you have a bay. I mean, do a quick calculation on the volume of it, what the turnover is, rain. I mean, it's literally a drop in the ocean. I mean, do a calculation what the volume is versus how much we're taking out.
Yeah, and the other thing is you should like put the salt you're like expelling like in a different place, right? Because if it's close to the intake, you're taking like...
Yes, yeah. That cartoon, I don't know if you think, I stole that. I don't even know where I got it from. You know, but I stole that image, yeah. You know, it's diffused and it's not right next to the intakes.
Yeah, and the second question was, with the electrical technology, are you able to like select the ions you want to capture?
I didn't go into, but we have done through membranes and resins and all, we do have selectivity. We can do just a multivalent versus monovalent fairly effectively. Multivalent means things that are more than one charge, so calcium, magnesium. We can preferentially do like monovalent first, so sodium, leave behind the multivalents, and then go into a second system to get them. So we can do separations of classes of molecules. We can also do things where we could put a membrane called a bipolar membrane that just say, we'll let the cations out but keep the anions in. So just say remove the sodium but retain the chloride as an example, and then go to a second system. So we have a lot of ways to manipulate it, but then that would become an engineering talk, and this would be a 2-hour talk instead of a half-hour talk. But yeah, those are the types of things why we say there's advantages which Professor Cohn in reverse osmosis would never be able to do.
Thanks, Seth. I think that we have come to the end of this session of Seth Snyder's presentation. And what I suggest we'll do now, I'll hand the mic to Aaron, my colleague, to make some concluding remarks. Thank you, Seth. Thank you very much.
Aaron, the floor is yours.
Yes, thank you. I'm just going to say a few words here. We're close to the end of our time, unfortunately, but I wanted to recap some of the discussion we heard during the day. So we started with the perspective of a common framework and common challenges for water, with the central question, is water viewed best as a right or a need? And based on all the discussion in the afternoon, I would also add to that the economic issues associated with water. So we can also see through many of the talks that food, water, and energy are inseparable. So for example, that you obviously need water for irrigated agriculture in the desert. You heard from Seth that we also need water to produce energy and energy to produce clean water. So you can't separate these things, and it's recognized that feeding the world is really a water challenge. Security of our energy resources is a water challenge. So we're really looking at the intersection between drinking water, water for food, water for energy, and water for industry. We also see that there's a common set of challenges in terms of transboundary issues, that water doesn't respect boundaries, that people's needs don't align with boundaries, and you have a very common challenge both of water management, on the one hand, how we practically manage the water that's available, and on the other hand, how we achieve some social equity both within countries and then across boundaries as well. So we've explored some solutions, potential solutions for these approaches, both from a social perspective. We heard the legal, regulatory, and political barriers to a successful management of water to best meet people's needs. I'll use that word, needs, or rights. And also some technological solutions that could potentially be implemented to help resolve this problem. All aspects of the problem, to use water better to produce food, to secure energy resources, and to deliver more water, to expand the resource base. So now we're talking about the opportunity for completely new types of solutions, not having to go through centralized infrastructure, through centralized governmental management, which has been the case for the last 100 years, essentially, most places around the world. But now having the capability to deliver water where it's needed with the quality that it's needed, and having the opportunity to look for higher efficiency and resiliency and sustainability of solutions. So in principle, this could address some of the challenges. If you can actually have people producing clean water where you need it to grow food, with precision agriculture to make sure it's used most effectively, could be much better. But of course, we have a huge amount invested in centralized infrastructure. You've heard this story in Israel, elsewhere in the Middle East, and in the US. So we're looking at innovation that can really integrate new methods with old methods and really coordinate in a much better way to address all of the potential concerns with water, right? To greatly expand the resource base and deliver resources where they're needed. So I hope you have learned something today that's useful, both in terms of your interest in the Middle East, and also you see a lot of threads of discussion that are more local to the US and to Chicago. So I hope you found it useful. Thank you.